the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 51, where today we're joined by another special guest, Dr. Saeed Rastagoo from York University. So Dr. Rastagoo is a quantum gravity theorist, I will say. To be honest, he was introduced to us in episode number 49 by Mr. Paul Delaney himself. If you guys have not checked that episode out, be sure to check it out. It's a really cool episode. And yeah, so we had a few questions on string theory and, loop quantum gravity and all these interesting theories in quantum mechanics. And that's when Mr. Delaney told us, well, you need to check out my colleague, Dr. Rastagoo. So here we are. So Dr. Rastagoo, maybe you want to take this opportunity to introduce yourself to our audience, just what you do at York University, and just a little brief history of yourself.
Thank you very much. It's very good to be here to talk to you guys. I'm an assistant professor at York University, working, as you mentioned, in quantum gravity, classical and quantum gravity physics, black holes, cosmology, all this sorts of stuff. I started at York University from January 2020, and before that I was an assistant professor at Monterrey Institute of Technology in Mexico, and before that I was postdoc in several places. So that's a short introduction about me.
Perfect. And so before we actually get into the questions, I'm going to mention the comment of the week, which we are not forgetting to do, as we almost did last episode. Yep. And so this comment actually comes from Golda, long-time listener. Thank you very much. And she says, your podcast make my week a whole lot better.
Oh.
So thank you so much. We know you listen to it every single week, and we appreciate your support. So yeah, if you want to be the comment of the week, make sure to leave a comment on YouTube or on Instagram at math.physics.podcast. And we will not forget. This is now going to be a weekly thing where we pick a comment and we will read it in the beginning of the podcast. Anything else, Ray?
Yeah. Some news for the podcast. Just some updates. Not really any news. We have hit 70. I think I'm not sure if we mentioned this, but we crossed 70,000 downloads. We're now at 73,000 downloads, so it's pretty impressive. And our follower count is right now at 5,700. So it's actually growing pretty well. It's going pretty well. Thank you, everyone. Yeah, so thank you everyone to continue to listening to us. It's a lot of fun to do. Right?
Yeah, make sure to follow us wherever you're listening to this. And enjoy the episode.
Did we not also hit, I think we also hit like 350, 380 YouTube subscribers, right? Or something like that?
I think
we hit another 100. We hit another 100, which is nice to see. We're growing slow, but we're growing, and that's all that matters, right?
Yeah.
So perfect. I think we can get straight into it, and the classic way we start every one of these episodes with any guest on the podcast with the classic question. What got you, Dr. Rastagoo, into your respective field? Like, was it something in high school that triggered you and said, hey, I love physics? Or was it an experience? Like, what was the situation? And what was your transition from, I don't know, maybe like liking physics to liking, quantum mechanics? Like, what was that experience like?
Yeah, so my answer, the first part of answer might be a little bit cliche.
Okay.
When I was a kid, my mom used to buy me kind of small scientific books, maybe a few pages each. I remember two of them. One of them was black hole, the other one about black holes. The other one was about dinosaurs. So it turned out that I liked astronomy kind of and black holes more than dinosaurs at that age. I started reading some sci-fi stories, about physics and space and all those things. And at some point, one of the friends in high school told me that, okay, it's all nice and fun, this sci-fi stuff, but real physical stuff is also, you have to learn about real physics also. Kind of as it was a nice suggestion. So I started gradually getting into more physics. I mean the mathematical physics and theoretical physics. I remember I liked the modern physics course in high school really a lot. And then I got more into astronomy, so I created a astronomy club, if you want, in my bachelor years. It's called, it was in Persian, the name was Persian, but it was called Big Bang, basically. In Persian, it's translated to Meh Bang, so Big Bang. And then we built 3 telescopes. Actually, before that, I built a telescope myself, a Newtonian telescope.
Oh, wow.
Yeah, so you can build a mirror and all of those things with some simple chemicals and some material like that. Then I mean you can polish the mirror using
of course.
those.
Yeah.
And then I created a 15 centimeter telescope, Newtonian, and then together in that group we created a 20 and 25 centimeter ones, two of them, and we had numerous observation nights. I remember that it was a really fun time. So gradually my interest changed from astronomy to cosmology, from cosmology to gravity, basically, and then I found, I mean, in my opinion, I found that what is the hardest and most interesting problem in physics is probably anything combination of quantum theory and gravity, and that's basically quantum gravity. So,
wow.
Yeah, that's the story.
Yeah, so we don't really, we're kind of sitting side by side with our audience right now. We don't know much about loop quantum gravity or quantum gravity or anything like that, but we did take an introductory course to quantum mechanics, so maybe we will catch like a little bit of the terminology here and there. But can you give us kind of a big picture explanation of loop quantum gravity?
Sure. So probably we have to start from a little bit before that. So a big picture of what we know in fundamental physics. So we know that the universe is made up of two parts, basically. One part is matter or matter fields. The other part is space-time. So space-time is the arena where matter fields interact and move and all sorts of things. And many times when people talk about universe, they forget that the one important part of the universe is space-time. So they talk about universe ending, and by that they mean that some sort of things happen to matter fields, they disappear or something happens, but the space-time is still there. So anyway, so there are two parts to the universe. The first part, which is the matter field or the matter fields, that part is explained by some theories, for example, electromagnetism describes the particles that have electric charge. And then we have 2 other theories, weak theory and a strong theory. They basically describe how atoms in more high energetic levels behave and interact. So this is about matter field. So previously there were classical theories, like electromagnetism was a classical theory. And people found out that you have to do something to these classical theories so that they match the observation. And that framework that they use is called the quantum theory. So they found that, for example, light comes not in a continuous system or way, but it's divided into small, what we call quantas, small packages or packets. So it worked well for matter field, and very good. We have the standard model of particle physics and everything. On the other hand, gravity or space-time, we have everything is classical. So we know what is space, what is time, and people have started to think about that. Okay, so what happens if we want to do the same quantization to the space and time? So maybe space itself comes in packets or atoms, and time itself. So they started to do that also to match these 2 theories of matter and the space-time together, because you cannot match 2 theories that one is classical, one is quantum. They cannot interact, basically. So that part that you want to quantize a space and time, or a space-time, is called quantum gravity. And the reason is that the field of gravity is actually a space-time. So you don't have gravity or a space-time. You don't have gravity and a space-time. Gravity is a space-time. You can think of the universe as matter fields and the field of gravity, or matter fields and the space-time. So the gravity and space-time is the same thing. So when people talk about quantum gravity or quantization of gravity, they mean quantization of space and time. So this is the big picture of what we have. Then, so we can later go to what is loop quantum gravity as opposed to string theory or other theories. But if
think,
you want,
yeah.
we can discuss about this. Yeah.
Yeah, so before we actually get into the loop part of the quantum gravity, just wondering about the class. So I think I don't know if this is still a question asked, but at least like when I was still searching up like my limited knowledge, I think there was always that big discussion whether gravity could be a particle, hypothesized as the graviton. So does quantum gravity support the fact that gravity is a particle, or does it? Because you explained that gravity and space-time are basically synonymous, right? So if that is true, then how could gravity kind of be conducted via a particle? Maybe I'm misunderstanding this. Maybe you can clarify. But
No, no.
what's the situation there?
Sure. So imagine, let's first start with a known field, which is electromagnetic field.
Okay.
So in electromagnetic field, you have a bunch of, so this is how field theory or quantum field theory works. In classical field theory, what you have is a bunch of particles, say electrons and protons, and then around them, they create a classical field. And by field, I mean something that is around an electron, for example. We don't know what that thing is. But whatever it is, it covers all the space around one electron. And if you put any other electron or proton in there, it feels a force on it. And that's the result of this field, that this is the invisible hand of the electron that reaches out to other electron and acts on it. Quantum field, so in this picture, you had two objects. You had field and particle. One of them is like a wave. The field is like a wave in the sense that it is not non-local, if you want. It's always all around the electron. The other one is a particle, which is electron and is local. Now, quantum field theory changed this view a little bit. So it says that you only have fields. There are no particles in principle. These fields are fluctuating because of the quantum phenomena. We can talk about that later. But anyway, so they're just this going up and down, so these bumps and valleys in the field of the electric field, like the water in the pool. So sometimes they're small, going up and down in the water. And at some point, for some reason, some of those bumps become permanent. So there are excitations in the field. And then those excitations are particles. So particles are made up out of this continuous field. And then they affect the field, and field affects them. And how these suppose that you have two electrons, how do they communicate? Because it's a quantum field theory, you really can't have these continuous things like fields. So what happens is that around these electrons make the field also excited around them and create another types of particles, if you want. And those types of particles are called photons. So those photons are force holders of the electric field. How do they work is that one electron is here, it kind of, well, this is very hand waving. I mean, it's not very, I don't want to go to very technical things, but so this electron creates out of the field around it, creates a photon, for example, excitation. And this photon travels from electron 1 to electron 2 and affects its velocity or momentum. And then either repels the second electron, the first one via this photon, repels the second electron or attracts it if it's a proton. And that's how this is the picture of quantum field theory. So everything is basically a quantized field, and particles pop up and pop in and pop out of this thing. And that's why you also have the idea of creation and annihilation of particles, which you don't have in quantum theory. You have in quantum field theory, but you don't have it in quantum theory.
Oh, those are different things.
Yeah, there are two different things.
Okay.
So this is the picture of quantum field theory of matter fields. So this is what we know about the matter fields. In gravity, if you want to have this picture, again, you have to quantize this. And quantizing the field of gravity, as I mentioned, is basically quantizing a space-time, right? Because what you see as a force of gravity is nothing but the curvature of a space-time. So we've interpreted as force or field of gravity, but it's just a space-time, no bending. So you have to have this quantum field that makes quantum excitations and blah blah. So this force carrier that I talked about in the case of electric field with the photon, this in the case of gravitational field, if we had the quantum theory of gravity, would have been the graviton. So A mass creates a graviton around it, and then send this graviton to another mass, and then that affects the other mass and attracts it. Unfortunately, or maybe fortunately, I don't know, for us, it's good to have to not know some things in physics. This doesn't work. If you try to quantize the force of gravity like that, or field of gravity like that, you encounter lots of infinities, if you want, or unknown parameters that you can never get rid of. And technically it's called the renormalizability. So you cannot renormalize the field of gravity. It means that there are infinite number of parameters in there, infinities there. It doesn't work. It only works, this interpretation only works if your gravitational field is very weak. So you have a small curvature. For that, you can approximate something as graviton, as a particle, but at the heart of black holes, or the situations where curvature is very large, that description breaks down.
And I was doing a little bit of reading, and the first line when you search up for loop quantum gravity, it says that it's attempting at consolidating quantum mechanics with general relativity. And so kind of what are the missing pieces there between the two, right?
Yes.
Like what do we need to connect the two?
So with regard to this question, and continuing from what I said before, so why is the reason that this description of graviton and quantizing the gravity in the traditional sense that people quantize matter fields, quantum field theory, doesn't work? The reason is that, technically it's renormalizability and all of those things, but you can also see it in this way. In order to quantize gravity, you have either quantized the whole field of gravity, or assume that I'm going to divide the gravitational field into two parts. One part is called the background, and the other part is called the foreground, or the perturbations. So this is actually what you do when you want to quantize other material fields. What you have is that you have a classical background spacetime, and these matter fields or matter particles are moving on this spacetime. And that background spacetime is just there, doing nothing basically, and it's very nice, and it's not quantized. And then you have a background on which you can quantize other matter fields. However, in gravity itself is the background. So that is the first thing, that on what are you quantizing thing, and what is this supported? As you see, this is the first probably kind of an issue. The second thing is that gravitational field or spacetime is the causal structure of the universe. So without the space-time or gravity, you don't know what happened before, after, at the same time, what causes what. These all lose their meanings without the gravitational field. And then if you don't have that, you don't have science at all. So if something causes something. Now, when you quantize the gravitational field in this way, the whole gravitational field, conceptually you are quantizing the causality. So what causes what and what comes before and after becomes jiggly. So really at the quantum level, you don't know what's happening there. So the first attempt was that, okay, let's take the gravitational field, divide it into a background, which is classical, and some small changes. Let's say the background is a flat spacetime. And a little bit perturbations, like when you put the sun on the flat spacetime, you get a little bit of bump or something like that, or valley. And then take that as a perturbation. That perturbation, you can quantize that then. So the background is classical, the foreground is small perturbations. You quantize that, and those perturbations become gravitons, right? And so the problem with this is that you have some sort of you're not really quantizing the whole spacetime, and it really doesn't work when you want to quantize the gravity close to the heart of a black hole, for example, where curvature is very large. Because this thing that I said, that you divide things into background and perturbation, only works if your perturbations are very small. That's the definition of a perturbation. But close to the center of a black hole, the gravitational effect is so large you cannot do that. So first of all, it doesn't work like that. This is one of the missing pieces. So that you mentioned. So you have to quantize the whole system, and this is technically called non-perturbative quantization. So as opposed to perturbation, dividing things by background and perturbations. And this is the main feature of loop quantum gravity, that it quantizes the full gravitational field. So it's valid at any energy or length scale, even at the heart of the black holes or closer to singularity.
So maybe now I think would be a perfect time where you can explain the loop part of loop quantum gravity, right? Because I'm just thinking about how you're describing how quantum gravity is aiming to, explain all parts of the universe, and black holes isn't one of them. So does loop quantum gravity explain gravity inside a black hole as well?
Yes. So
Oh,
first of all,
okay. So maybe you could, yeah.
yeah. So first of all, let's we will discuss about, if you want, about the differences between different theories of quantum gravity. So, but in general, quantum gravity means a theory that quantizes space and time. So in loop quantum gravity, the first feature is that some of the features actually are that you don't have you don't have higher dimensions because you don't need them at that time, at least when you want to start quantizing. And also you don't have additional ingredients like supersymmetry and all those things. You start just with plain quantum theory and in a general sense, and gravity. So let's start with gravity. So suppose that I want to know if there is gravitational field somewhere or not. Okay, this only can be known by doing what physicists called something that is not local, some measurement that is not local. As an example, suppose that somebody puts me in an elevator, very small elevator, small room, and releases me in the space. Now, in order to understand if I'm just free, basically if there's gravitational field around me or not, there's no way to do that in a very small local neighborhood of me. So I can never know, because everything around me is accelerating with the same acceleration, and whether there's gravity or not, I cannot know that. However, if I move around, so I measure the direction of the, if you want, force on me in some position, and then move around like 200 kilometers away from that small room, and then measure the force on me, I may see that these directions are a little bit different. So suppose that Earth is here, and the direction of gravitational field here is towards, if you want, toward the southeast, and in the other position is towards the southwest.
Yeah.
Right?
Yeah.
This is only possible if you go from place to place. So your gravity is only known if you move around. Now, how you interpret this in mathematics? You take a vector with yourself. Okay, so you know that the vector is basically a line with an arrow with a direction, and you start from here and go around the loop in a space and come back. And if that vector comes back exactly in the same form without any angle with the original vector, you say that there is no gravitational field in there.
Wait, sorry. Could you define loop a little bit better? Like when you
just
say
start
loop,
from one position.
Just a connected path, right?
Yeah,
Just
so
like
you start from.
it's like a
it could
360
be
kind of.
exactly. You go some 200 kilometers. It doesn't really need to be actually a circle. You can go like a triangle. You can go a square. So.
But do you need to return back to your original
Exactly.
path? Okay.
That's the
Okay.
definition.
Okay.
Yeah. So.
Okay.
So you return back always to your place, and this loop should be finite. At the beginning. So you cannot do it really locally at that exact position. So if you go around and come back, and the vector that you have in your hand is the same in the direction and the magnitude, you say that there's no curvature in the space-time, and because there's no curvature, there's no gravitational field. But if you get back and you see that, oh, it changed, so that's the definition of existence of gravitational field. That's actually what people call the Riemann tensor. The Riemann tensor tells you if you go around the loop and come back, the Riemann tensor is non-zero if your vector changes, and it's zero if your vector does not change. And the Riemann tensor is the essence of gravitational field. Okay, so you already see that there's a loop here.
Yeah, you can already hear it.
Yeah. So now in another, so from the quantum theory on the other side, on the other hand, we know that there are some certain loops that have all the information of the field in them. So in order to know about the information about the field, one way is to just study the field itself in some method, or you study just the loops in that theory. And if you have all the loops associated, the numbers associated with those loops, you can have information about the field itself. So loop quantum gravity does this. It uses, these loops are called Wilson loops in quantum field theory. So you study all the possible loops in space-time, And then you see that, okay, with all these loops, I can have information about the gravitational field. And then you quantize these loops, basically. And this is the simplest explanation I can tell you about the loop quantum gravity. This term loop comes from. So you can quantize these loops, and this is equivalent to quantizing the full Riemann tensor, the full gravitational field.
But wait, so these loops, how would you? Sorry, I'm still thinking about all of this because it's so interesting, but it's still like so much out of our scope because I'm thinking about. Okay, first of all, just a little backtracking here. What exactly is quantizing? Because you keep saying quantizing. Like I kind of understand the concept, like, okay, we have something like in a macro scale and we want to, I guess, quantize it to apply like theories of quantum mechanics or something to that. Maybe some sort of that I understand. But like theoretically, mathematically, what does it mean to like, okay, I have this theory, I quantize it? Like what exactly is that?
Yeah, so let me tell it on two levels.
Okay.
And the first level is just more conceptual. So basically means that introducing uncertainty in your variables, quantization. So before introducing quantum theory, you can measure the position and momentum of the particle at the same time and as precisely as you want. But after quantization of the theory, you cannot do that, as you know. So one of them, the increase in the decrease in the uncertainty of measuring something increases in the other one. A little bit more technical is that if you're a student of physics in maybe third year or higher, you know about this thing called the Poisson bracket. I don't want to go in detail about that, but basically it means that how these two x and p compare to each other in classical theory, they can be just measured as more precise as you want. When you change this Poisson bracket into the quantum bracket, you cannot do that anymore. So you have seen this famous bracket of Q and P equal to IH bar or something. So classically, it's just Q and P equal to 1. But then, it's a little bit hard to explain without any math. So basically introducing uncertainty into your variables.
And basically, I wanted to ask you as well about string theory and why maybe some people go the loop quantum gravity route and this, or sorry, I'm not saying this well, but whether some people prefer going the loop quantum gravity route or the string theory route, and maybe what's the difference and like a general comparison.
Because to my knowledge, I believe that obviously you can correct me now, but like to my knowledge, like string theory, like the attempt, now what it's become is very different, but the original idea of string theory is very similar to that of loop quantum gravity, right? Like they're both trying to find this perfect theory that explains the universe. So
there are a few differences. First of all, probably I would say that with the lack of experimental evidence that we have, unfortunately, the only thing that we are working on physics, so ultimately what makes a theory correct is not if it's beautiful or appealing, but if it matches the reality, right? So we don't have that. So basically, people have some kind of, if I may, philosophical appeal to some theory. So, for example, loop quantum gravity comes from the gravitational physics community. So it's really people in this field really think about background independence in the sense that I mentioned. So you don't have a background and perturbation on it. You just have to have the full thing quantized. There's no background, which is very beautiful. Makes things. There are lots of symmetries there, and you're thinking just about quantization of the gravitational field, right? So you make the space-time kind of quantized in the sense that having the atoms of a space-time, like when you quantize a gas. Think about the gas as a quantized thing, and you have atoms of gas which are the atoms, as you know. So the same continuous space-time may be having these atoms if you look closer. This is loop quantum gravity, basically. And string theory comes from the field theory part. So people who work on, as I mentioned, remember the matter fields and all those things. So the idea behind that is that the basic idea is that unification of all forces or all fields, gravity and all other fields. Via another field. So the field that they have in mind is a string field, So they are, instead of one-dimensional objects that are particles, they have, zero-dimensional objects that are particles, they have one-dimensional objects. They're moving around, and somehow gravitational field and other fields kind of emerge from their interaction. So this, as you may have read a lot about the string theory in science, public science books and documentaries, these strings move around and they have excitations, so they're like jiggling around. Different excitations have different energies, and those different excitations or energies correspond to different particles, electrons, protons, quarks, all those things. So the difference is that string theory at least starts with perturbative method of quantizing or a field of gravity. And so whether you believe or you like to have unification rather than just quantizing of gravity and background dependence, so that you will go to one of these fields, and in my opinion you can find kind of truth in both or many of these theories of quantum gravity, and ultimately people have to talk about this together, these communities, and find shared components of quantum gravity to be able to build the final theory of quantum gravity.
Yeah, I was listening to a podcast where they were talking about string theory, and they were saying how like string theory is a lot of just mathematical gymnastics with nothing really to back it up. And people are saying, "Wow, look at all this math I can do," but then there's actually no real like proof of it being proof backing it up.
Mm-hmm.
And yeah, I mean, I definitely think that the engineering side of all of physics is what powers our theories, and the better our tools, the better our observations, the more information we can really extract from the entire universe. And
do you mean experimental side? You said engineering side. I'm like,
yeah, well,
like more experimental right?
side. Yeah, but also you need to having the technology and building the new, we don't know what our tools are going to look like.
I guess that would be
1,000 years, right? That has a lot to do with engineering, as well as I don't know if we talked about this on a previous episode, but in terms of space travel and things like that, there are a lot of, well, this is of course a little bit speculative, but with extraterrestrial technologies showing proof of gravitational propulsion and things like that. Imagine if we had public access to these kinds of feats of engineering. I think it would really power our abilities to come up with better theories that really do explain every corner of the universe.
Yeah, definitely. Technology is very important. I don't think that anybody on Earth has this technology and to test quantum gravity theories and doesn't share it, because this is simply, it's not possible basically. But the problem with testing quantum gravity theories is, as we mentioned, technology or engineering. The problem is that the energies you need are really, really, really high. I mean, unbelievably large energies. So basically what we have at the moment is the experiments are at the level of quantum field theory models, basically in particle physics. So still really high energies, but compared to quantum gravity scale, orders of magnitudes lower. That's unfortunately one of the things that we have in quantum gravity community in general, and that's why you have a variety of this zoo of quantum gravity theories that no one knows which one is correct, and many of them are really beautiful theories. So you don't have only loop quantum gravity and string theory. You have causal sets, for example, that assume that the basic structure of the universe is not a space or time or matter. It's just basic causality, and out of that they can make up a space-time. They have other theories that out of a Hilbert space or a quantum space, which is an abstract space, they want to build up a space-time out of that with something that called entanglement. Probably, maybe some of you, your audience knows about that because of this spooky action at a distance.
Yeah.
So there's so many theories like that, but we really don't know about them because we don't have experiments doing that. It's the same as situation with multiverse, wormholes, all those things, or even what you mentioned about the engine of these objects that can move even faster than the speed of light. There are actually papers on that. The warp drive, actually. So yeah, the problem is the experiment and the really high energies that we need to test this.
And do you think that maybe one day, this is speculative, of course, but one day we're going to find a theory that, it's so beautiful and so complete that you can just derive, like, every single theory that we know now. Like, every theory, every classical quantum theory that we have now is just a subset of this magnificent theory.
Well, the universe never ceases to surprise us, so I don't know. It may be the case.
Yeah.
And the history of science shows us that beauty is not enough for theory. It's really good. I mean, there are many things that are really beautiful in science and work. But ultimately, the universe doesn't care about this, so it should work in the universe. And that's the idea of what you mentioned, is the idea of unification. So if we have a final theory that have all other theories in it, in principle, you're able to get all the other theories out of it. But it's not that simple. Also, even if you know the fundamental theory, and if unified fundamental theory, suppose that I give you the fundamental theory of particle physics at the moment, at least, which is the quantum field theory. No one is ever able to explain the work of heart. You're using that quantum field theory. There's several levels of complexity, and you have to have effective theory. So, for example, biology is an effective theory, which is valid on the level of meters and centimeters and all those things. And it's really hard to really derive it from quantum field theory, but we know that it's basically derived from there. So it's true and not true at the same time. So in principle, you can do that, but...
Yeah, that's right. And also, there's kind of this mystery aspect, right? Where you say, you could present to me a theory, and it's like, okay, well, now explain consciousness.
Oh, that's another story. Yeah, consciousness is really what that stands out. I'm not a philosopher, obviously, so what I say, just take it with a grain of salt. But about the qualia, which philosophers talk about. So basically, the feeling of, so you see something that is red, and that the redness, the feeling of redness, or the feeling of warmth, cold, all those things, these are really challenging to explain using physics. I'm not saying that it's not not physics, but just different viewpoints on that. And this is really it's called the hard problem of consciousness.
Yeah, and at the end of the day, everything that is in the universe is natural and is a consequence of, the initial conditions of the universe just evolving over time. And so there is, I hope that there is an explanation to most of the things that we see, and especially like consciousness, at least in our local universe here on Earth, is so like widespread. You see so many different types of like animals and whatever, and they seem to be pretty conscious. I mean, at the same time, there's no way for me to tell that anything else is really conscious, but this is getting really into the philosophical side. I really, I don't know, I have hope for the future of theories and explain the ability to explain things.
Yeah, exactly. That's the hope that we'll live by in science, at least.
For sure. And so actually now we are coming up on 40 minutes, and to anyone listening right now, this is the very first episode where the Math and Physics podcast is sponsored by Brilliant.org.
Oh.
So this is a very monumental moment for us right now. And so if you've listened to this podcast up to this point, you are obviously interested in math and physics. We know that not all of our listeners are in the science streams, but are still, of course, interested in the topics that we cover in this podcast. So if you actually do want to learn more about these topics in your free time, Rehan and I highly recommend you go and check out Brilliant.org's online educational courses, where you can actually build up your knowledge in math, computer science, logic, and applied sciences, and more, all from scratch. We know that some of you aren't even in university yet, but want to learn all the topics taught by the website. And of course, Brilliant is the perfect place for you. Rayhan and I have tried it ourselves a little bit, and you can really start from zero and learn all of the things that Rayhan and I are learning in university right now. For example, you can start with basic algebra and work your way up to multivariable calculus, which is what we're learning right now.
A lot of people have actually asked us, hey, I'm in high school, like, you know, still in grade 10, 11, and I'm really interested in the stuff you guys are talking about, but I don't really understand mainly, or like everything, you know? So Brilliant is actually legitimately a place where all of this is very readily accessible. And it's actually, and it's also very apt that we have a partnership with Brilliant, with our podcast, you know, promoting science and promoting STEM research and stuff. And I mean, that's basically the idea of Brilliant too, right? So we're also very happy to say that for our first 200 listeners, like the first 200 people that want to get a Brilliant, what am I trying to say?
A membership.
A membership, that was the word. Yes. So if you want to get a Brilliant membership, head on to brilliant.org /MPP. That's the Math and Physics Podcast. And for our first 200 listeners, you will get 20% off your premium membership. So yeah, that's just something that I think is really apt for our podcast here. And once again, thank you to Brilliant for sponsoring it.
We're gonna put the link in the description.
Absolutely,
so
absolutely.
Check that out.
So, Dr. Rastagoo, have you heard of Bob Lazar?
Yes. Oh, we are going that way. Okay.
Yes. Let me ask why. I mean, let me explain why. Because we were talking earlier about the possibility of, you know, I think Parker was mentioning, like, you know, these instruments, these engineering instruments that could far exceed what we know today. So my question is, well, to those people that don't know that don't know Bob Lazar, well, he's kind of like he's a physicist that works in an area kind of off. What's it called, Parker? I think you know. It's
Area 51. Okay? It's a laboratory.
It's called S something, right?
S4.
S4,
At
something
Los
like that.
Alamos.
Yeah, and he was on a Joe Rogan podcast where he was talking about a lot of his experiences with anti-gravitational machines. Now, I heard that and I just flipped. I'm like, no way that's possible. So I guess my question here is, well, first off, do you believe he's telling the truth? And second off, if you do, if it is true, what do you think that would have an impact on our understanding of quantum theory?
And also, sorry,
Yeah, go ahead.
just to add another question, with all of your years of study, is there any indication towards an anti-gravity particle or
Something like
thing?
that, yeah.
Right, yeah.
Okay, so that's the first question. I don't know if he's telling the truth or absolutely. I don't know him. I don't know anything about. So that's I cannot answer the first part. The second part is about something we call anti-gravity. So that's based on the interpretation. So for example, if you look at the paper that's called the warp drive by Miguel Alcubierre he's also in Mexico. That was I think the first paper published in putting this warp drive into physical context. So it basically gives you formulation of that. Of course, there are some serious issues with that. You need some exotic mass or exotic matter for that. But I mean, people at least at NASA took it seriously to kind of study that, work on that. Anyway, so because that's a scientific paper, I can talk about that. That paper tells you that given that you have this sort of weird matter, let's say we have it, you can create at the back of your spaceship and in front of it, basically put your spaceship inside a bubble space-time in which inside is different from outside. We have something gravity is called metric, and the metric basically is the gravitational field, if you want. This metric, as I mentioned, this is very, very interesting. That gravitational field. Sorry, I just digressed a little bit. So the gravitational field, as I mentioned, is the space-time and its causality and all those things creates all of that. So the metric is all of these things at the same time. The metric tells you what is the distance between objects, what is the time distance between the space distance or the space-time distance, and all causality and all of those things. That's why it's called metric, right? It kind of measures the distance, if you want. So this metric or gravitational field, you can modify just around the spaceship such that outside you have just usual, if you want, flat space-time, and inside you have some sort of curved space-time. And the metric field or gravitational field behind the satellite or that object is kind of, if you want, positive or so it's pushing the spacecraft, so creates a positive what is the word, hill, if you want, and in front of
I think the analogy is that if you have like a marble on like your bed or something, and then you press down in front of the marble, it'll start accelerating. And then
so you have to bring the gravitational field up at the back of the spaceship and create a valley in front of it, so that it constantly moves forward. But the beauty of this is that what is moving is actually not the spaceship itself. The spaceship inside its local space-time, so that bubble is just sitting still doing nothing, and that bubble itself is moving around, that bubble of space-time moving inside the exterior space-time. And this has really nice at least two really good advantages. One of them is that there's no problem with acceleration. So because one of the problem with space astronauts and all of that is that our body cannot take that much acceleration, maybe 10 Gs, or I'm not sure how much, but that's some sort of like that. So even if you have the technology to reach this close to the speed of light, you can do it. You have to do it very slowly if using traditional technology. But in that case, you are just sitting still there and you are not moving. The space-time is moving, so you don't feel acceleration. So you can immediately go from 0 to close to the speed of light. The second thing is that because the space-time itself can expand or contract or move around, if you want, with any speed it wants. So it's not bound by the speed of light. So you can just move around even faster than the speed of light. And from the viewpoint of somebody that is close to this spaceship, you can think of that you can think of that as either gravity or anti-gravity, because it's just moving weirdly, right? So that is a problem of interpretation. Maybe that's true, but it's not really anti-gravity. It's just gravitational field itself, but you can manipulate it in weird ways.
So technically the warp drive is not really breaking special relativity then, because just hearing the word warp drive, you're like, oh, superluminal, but that right there would break all the laws that we've been brought up with, right? So so would it work in such a way where, because you were describing like we're creating more space, and technically like that wouldn't break special relativity. Like how would a warp drive exist? Basically my question, I guess I can form, is how would the warp drive exist without breaking special relativity?
So it is basically based on general relativity, which is it's a more complete theory than special relativity. So in general relativity, you have all those things of the speed of light and blah, blah, and then you also have these additional things. You're creating this warp drive actually using general relativity. So basically the theory is relativistic completely. The problem, or actually the advantage is that what is moving around is not really the satellite or the spaceship with respect to its immediate spacetime. It's the bubble spacetime with respect to the outside spacetime. And we know that is absolutely possible. We see that the high redshift in cosmology, things are moving apparently faster than the speed of light, but that doesn't mean that they're really moving. The matter is moving faster than the speed of light. It's just a space-time itself, and then drags the galaxies and all of those things with itself. So it's absolutely possible not to violate special relativity or general relativity because you are not moving material objects faster than the speed of light.
Oh, wow.
So all we have to do is figure out how to do that.
Yeah, so if you want to basically curve a space-time around the spaceship in a certain way, there's a issue in that. I will mention that, but basically you have to do that, and then that's it. You can go on. So the issue is that for that, at the moment, the theories that we have, the papers, you have to have some sort of, if you want, exotic matter with negative energy density or negative mass, if you want. So we don't have that. Even if you have that, you may need a lot of matter to curve a spacetime in that way. So the spacetime is like a fluid, but a very stiff fluid. In order to curve it, you know that you have to put a really, really large mass there, like a sun there or Earth, and so it's not easy to put in a small amount of space a large mass, because it creates a black hole. Then you have to deal with that, and so yeah.
Imagine accidentally you're like, hey, let's do this. Boom, create a black hole. Entire experiment just done.
I think entire Earth is done.
That'd be pretty funny.
But yeah, I just had a thought in my head, and maybe this doesn't really, or maybe you've never really considered this, but what about the explanation, or I guess the interpretation of a white hole in loop quantum gravity? Is that a thing?
Yeah. So this is something that in many models of black hole, interior of the black hole or black hole itself in loop quantum gravity appears. So what happens is that, actually it's one of our latest papers to study that in a different context. First of all, when a star starts to contract, it goes inside its Schwarzschild radius. If it becomes smaller than some radius, it becomes a black hole. Just have in mind that outside of a black hole, it's basically like outside of a star. Nothing special happens outside. So when you enter the black hole, the Schwarzschild interior, suppose that you ride on a sphere. So at any point, a shell of a sphere, we call technically two sphere in physics, because it's two-dimensional shell. So that is just moving towards the center of the black hole. Suppose that you're sitting on one of those shells. And for you, first of all, let me say something interesting. For you, it may take maybe 1 hour, 10 minutes or something to reach the singularity, classically. But for somebody outside, if the black hole is really massive, for somebody outside, it takes billions and billions of years. So that's an interesting thing. So in gravitational field, time slows down in strong gravitational fields.
Right.
So in classical gravity, what happens that you ride on this two sphere, you get closer and closer to the center of the black hole, and just you fall into the singularity, and that's it. You just disappear from physics, because that is something that curvature becomes infinite, and there's no mathematical way to deal with infinite. So if I tell you what is the 2 times infinite, it's infinite, but those are different infinites, all right?
Mm-hmm.
So it doesn't make sense. Infinity is not a number. That's why it's hard to work with. That's a concept. But in loop quantum gravity, at least what we know is that many of the models show that classical singularity in quantum regime changes to a highly quantum state, something like a graph. And those graphs are basic states of space-time in loop quantum gravity. And sometimes you can demagnify your space-time. You can decrease the resolution and look at that graph, and you see a smooth classical spacetime. Sometimes it's not possible. Sometimes there is no classical counterpart to this graph. And the thing that appears at the center of a black hole, where it used to be a singularity, is such a graph that is not classical. You can never look at it as a graph. It's highly quantum. So, but it appears that something happens there that, in principle, when you go towards the singularity, some kind of wormholes created there quantum mechanically, and then you bounce back, right? So at some point any trajectory bounces back, and whenever you bounce back, that means that you have a white hole. I will explain that a little bit more now after this. But so bounce back and you get out of the black hole. So the thing that always attracts you if you get inside its event horizon is called the black hole. Mm-hmm. And the thing that always spits you out, you can never go backward to, that's called the white hole. So it's the time reversal of black hole. Yes.
Sorry, could you explain the bounce back part? I didn't really get that. Like how?
Yeah, me too.
Yeah, because if you're going inside, how would you bounce back? Like, yeah.
Yeah, so you go inside and you reach the singularity, which is now a quantum thing, and well, humans cannot do that because obviously, I mean,
assuming.
Something happens at that regime, that quantum regime, that pushes you outside. So the equations show that there is, well, we get back to that, some kind of anti-gravity force, that is quantum effect. It's not really anti-gravity force. This is a term in your equations that has a, if you want, a positive sign. So the negative sign means that you're attracted, and positive means that you're repulsed outside. That positive term is always very, very small unless you get very close to the singularity. And then that becomes even larger than the attracting terms. So the repulsive term only comes into effect really very close to singularity and pushes you back. And when it pushes you back, you kind of bounce backward outside. Of course, the complete picture is much complicated than that. But that's the bounce back part. So this is a quantum effect, absolutely quantum. There's no classical thing in there. That becomes really large. Suppose that thing it goes with 1 over r, that force, or 1 over r to power 10, let's say. That is much larger than 1 over r squared of the attraction of gravity. So it's really pushes you outside, but only comes into effect very close to singularity, not far from it. So this is the definition of black hole, that when you go inside, you have to go inside, and white hole, that when you're inside, you have to come outside. And the reason is that when you're outside of the black hole, you have a space and time, right? You can go backward and forward in space, but obviously you cannot go backward in time. You have to go forward in time. When you go inside the event horizon of a black hole, space and time switch their nature. So what you knew as time becomes space, and what you knew as space becomes time. Basically, when you're going towards the center from the viewpoint of an observer from outside, that direction previously, before you enter the black hole, was a spatial dimension. So you go back and forth. But when you go inside, that direction is now time. So you cannot go backward, because you have to go backward in time. You have to go forward towards the black hole, and that is actually the direction of time that you're going. That's why it's a little bit very actually non-intuitive, but that's how it happens. In the white hole, they call the white hole is the time reversal of black hole. So that direction towards outside of the white hole is the positive time direction. So you have to go outside. There's no way you can go backward.
Do you believe?
Go ahead.
Oh yeah, sorry. Do you believe that we will ever be able to make an instrument that? Wait, how do I formulate this? That goes into a black hole. I don't even know if this would work, and is able to capture the singularity. And assume we can. How would that change our understanding of quantum mechanics near a singularity? Like, let's say you had the information, you had a picture of all the information at the singularity. Let's say, like, how would that help?
So let me first say that we don't know black holes exist or not, because I'm one of those physicists that I really like my theories and all those things, but at the end I trust experiments. So if at some point we experimentally know that there is absolutely no white hole, so we have to change our theories. Like Sherlock Holmes always say that, right? We have to change our theories to match experiment. Let's say there are white holes, and we have this bounce back and everything. The issue is that when you go inside the black hole and you bounce back, you don't bounce back to the same outside the space-time from which you entered. You bounce back towards another part of the universe, or even another, as they say, causally disconnected part of the universe outside another. So basically, you enter a black hole, there's a wormhole there, you go out and you go some other part of the universe. So in order to send something and get information from that, first of all, you have to find that thing where in the universe that is.
No, but I mean, I'm saying, assuming, I'm not actually asking about the white hole, because I know that brings up a lot more complications. I'm saying, let's just say there's just a black hole, and somehow we are able. Well, first of all, is it okay? I'm actually thinking, but the more I'm thinking about it, I don't think it's possible for us to put something in and actually get it out. But I'm saying, assume we have the information of the singularity of a black hole. Like, how would that affect or help our understanding of quantum mechanics near a singularity? Because this question is mainly motivated by a scene in Interstellar. So, I mean, I don't know if you've seen the movie. Yeah, so Interstellar.
That's actually a blackboard from Interstellar.
Yeah, I actually noticed something. I'm like, that's interesting. Yeah, so he said, I forgot, Ram says in a certain scene that if if we are able to image the singularity of a black hole, I will be able to solve all of these problems that we're dealing with. So my question is, if let's say we are able to image the singularity of a black hole, realistically speaking, would that actually help, would that actually help quantum mechanics? Would that actually help physics? And in what way?
So the thing is that you cannot take a picture of a singularity basically because that's a quantum regime. There's no picture or anything that these classical concepts don't exist there. But suppose that you could send a probe inside the black hole and somehow comes out somewhere that you can catch it.
Exactly.
All of those things, and can make meaningful measurements. This is basically like CERN or LHC. So you get some bunch of readings from, I don't know, depends on the theory. And for example, loop quantum gravity, we have this spin network graph there, so you can read the properties of those spin network. And obviously it tells you, even if the spin network actually is true or not, I mean, this viewpoint of loop quantum gravity. So that's based on your theory. If, for example, in loop quantum gravity, what the prediction is that, again, as I mentioned, so there's some sort of graph there.
Mm-hmm.
And so you tune your device to measure the properties of that graph. But other theories may have different things. So,
returning to white holes, does loop quantum gravity predict like a stable white hole? Because I've never heard of like if a white hole were to appear, it would instantly what is that, cave into a black hole, right? Because of the sheer like matter density that would just appear out of nowhere, right?
Maybe that's more true about wormholes. So white holes can exist as long as, again, let's go back to theory and assume that experiment doesn't matter at this moment. So in principle, if you tweak some things, if you have negative matter density and all those things, well, you can have both black holes and white holes, and they're connected by something called a wormhole. So there are stable wormholes if you can have negative energy density. Yeah, you can make them stable. There's no problem. Both of them, black hole and white hole. So again, if a black hole can be stable, so can a white hole. Again, in principle, with all those weird properties. The problem is that if you want to have a wormhole between these two, so to create a white hole, at least again, generically, you need to have some sort of energy density or mass, if you want, that is negative. And we don't have that. And even if you had that, you need a huge amount of energy to keep that the wormhole open, because it will close up immediately. It needs a lot of energy if you want to confront gravity, it's not to close on itself.
Mm-hmm.
So yeah, we haven't seen any white holes obviously now, but some people conjecture that these fast radio bursts that we see very far away in the sky could be white holes. But
so what do you? I guess you've already kind of explained that for a wormhole to exist, we would need some sort of exotic or some sort of negative matter, of on that scale. But well, my question, I kind of like twofold. Well, what does loop quantum gravity say about wormholes in general? And let's say we did find this negative matter, like, because I keep hearing, we can just construct it with negative matter, but would we not need, because like a wormhole, I guess, connects to spatial coordinates. So let's say we want to go to another galaxy. Would we not need to like place, quote unquote, place the other side of the wormhole over there? Like, how do we make that wormhole once we have that negative matter or energy?
No, you just need to, enter the black hole, and just when you're close to the singularity, just increase the energy. And
no, but does a wormhole require a black hole? Like, do you like?
Yeah.
Oh,
So
wait.
I didn't
wormhole
know
should
that,
be,
actually.
you need both sides. You need black hole and white hole. So that's the definition of wormhole.
No. I'm not talking about black holes and white holes anymore. I'm just talking about wormholes in general, like an Einstein-Rosen bridge.
I know, but
right.
So yeah, so both ends of these this wormhole should be something. So you enter from some part of the space-time, go to the other part of the space-time.
Exactly.
So if that if I understand your question, so you need that basically.
Yeah, so my
Yeah.
question is, how would we so we can't just place it in anywhere? Like, for example, simple example.
I think this is beyond the.
Yeah,
our
I know.
knowledge
This is
right
all
now.
very theoretical question. This is all very, very. This might not even make any sense. But I'm just trying to place the idea of a wormhole in my head, because I'm like, okay, let's say I want to go. I'm in Canada right now. Let's say I
Rehan,
sorry.
sorry. No, I was just gonna say the idea of the wormhole. You need an entrance and an exit, right? So
Yeah.
how do you even?
That's exactly my
place
question.
that,
Like, how,
right?
like if let's say I want to go from Canada to, I don't know, like India, for example. Like, I have negative matter. Let's say I have negative matter right here. How do I? Okay, I'm here, so I can make an entrance. How do I make the exit? Like,
Well, it will create. So you're asking me something technological.
yeah, I guess this.
And this,
I get-
even the theory is really
Yeah.
people. So basically,
okay.
the idea is that when you create an opening somewhere and you can keep the opening open using a negative energy density, and then there would be another opening on the other side, and you can go from this. But actually, this idea was developed, which is very nice. There's a really nice paper about that, actually for graduate students. But this idea was in 1988, I think, if I'm right. One of the famous physicists created this idea, wrote a paper as an educational paper for classroom general relativity, and
Oh, wow.
so it was really interesting. And then they showed that you need this negative energy density and all of those things. But one thing that I can say about that regarding to quantum gravity is that in order to keep that or what is related to this negative energy density is basically something called null energy condition. Null energy condition basically tells you that, or energy conditions basically tell you that your matter field is normal. There is no negative things there. So null energy conditions classically cannot be negated, basically, if you want. But again, using quantum effects, you can see that happens actually. So quantum effects can give you. So one of our papers, the recent papers is about the Raychaudhuri equation. So Raychaudhuri equation is the name of an Indian scientist. So it tells you that suppose that you have a bunch of particles on a circle and they're moving in a space and time, right? If there's gravity, this will contract and expand, or it will change its shape to an ellipse or from circle to anything. And if you have a singularity somewhere, this will contract and infinitely contract. So the rate of contraction would be infinite at some point. So that's where you have a singularity. Now there's no way to stop this unless you have a negative matter classically, right? However, we showed, for example, here that using quantum effects and without any matter fields, all these factors that contract these material objects, these lines, if you want to call geodesics, will be overcome by other terms we call effective terms, additional terms that come from quantum theory, that they actually oppose these classical focusing terms. So the defocusing term, if you want to call them anti-gravity, I don't call them anti-gravity, but these defocusing term appear due to quantum corrections. And at the singularity, instead of all these circular objects just going to one infinitely, focused, they kind of be repulsed, and then everything would be kind of normal and regular. So in that sense, you see that quantum things can kind of work for you as quantum terms, work for you as something that looks kind of like against the energy condition, null energy condition. So again, all hope is with quantum gravity, quantum
Yeah,
terms.
that's that. I guess that's the final answer, right? That's the final answer. Figure that out.
For sure. Well, I'm super excited for my career in physics, obviously, because there's so much to discover, and the like exponential curve of the advancement in technology, I think, is going to produce some amazing like, for example, I always say this, it's like explaining the internet to a caveman. We're gonna have that kind of like internet that will, even if you explain it to us right now, we'll be like, I don't.
Explaining quantum mechanics to a cat. Try
Yeah,
that.
Yeah. That's right. And also, Rayhan, when you were asking your question about the wormhole, I was just thinking, like, were you expecting an answer like, oh yes, you just plug in the coordinates into your wormhole machine?
Okay, I guess I didn't really think about what I was expecting. I was just thinking out loud, because I think the most common thing with a wormhole is like, where do I exit from? I think that's the question I've always had, because everyone always, the classic movie scene when they fold a piece of paper and they put a pencil through it. Oh, that's the wormhole. Like, that's the most classic scene. But I'm like, where do you get the other side from? Like, how do you find the other side? Like, obviously the entrance is where you are, but where's the other side? So I just had these questions that
The
I don't
first
know.
step is to just find a good theoretical framework for this,
Yeah.
and then we go for technology and find a place. But
Yeah, I think
first-
those would be the steps. Those would be the steps for sure.
So, yeah, we're coming up on an hour and 10 minutes, so I think we can end the podcast here.
I think so.
We thank you so much for coming on today.
Absolutely.
This was absolutely fascinating.
Eye-opening. I think we learned
Yeah,
so
for
much
sure.
today. This has been an amazing
sure.
conversation. Thank you.
good. Thank you for inviting me, and I hope it was not. Sometimes you lose the level of technicality. You want to explain things not too technical, but then it's so. I hope it's not. It wasn't.
Yeah, it's always hard to use like words that are simpler than the ones you're used to without going
I understand
overboard.
They
But
say
you
it's
know,
like explaining physics without math, especially this technical physics, is like playing one of Mozart's pieces with boxing gloves. So
It's a way to think about it. That's a way to think about it.
So yeah, if you enjoyed this episode of the podcast, make sure to follow us on Spotify, Apple, or watch this video version on YouTube. Leave us a comment, some episode recommendations for us, or just something nice on YouTube or Instagram at math.physics.podcast. Anything else, Ray?
I think you already mentioned our email, right? Just math.physics.podcast@gmail.com. If you guys have any questions, any queries, we're getting a lot of emails, and we love it. We love to respond to emails. Like we've always been getting, as I mentioned in that sponsorship message, like we legitimately got like 2-3 people asking us, hey, I'm in like grade 10. What do I do to learn more stuff? Like, we got so many DMs like that, and that's amazing. Like the fact that you guys want to know this, like that's exactly what we're trying to do here. Trying to spread our love for the science community. So yeah, I think that's it.
Yeah, so thank you once again, Dr. Rastagoo.
thank you.
And yeah, this has been episode number 51 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.